Okay, in this video we will be talking about polar versus non-polar molecules. All right, we've talked about polar versus non-polar bonds, but now we need to talk about how that affects an entire molecule. So let me just review the polar bonds really quickly. If we have like a carbon-carbon bond, for instance, those have the same electronegativity, so that is a non-polar bond. And that's because they have the same electronegativity, or delta En, the difference in electronegativity is equal to 0. Now, if we look at something like a carbon-oxygen bond, okay, this, we have a difference in electronegativity. And we can label this as partially positive and partially negative. So the oxygen, whoops, I don't know how that came up. Fun. Okay, the oxygen is the higher electronegative element. So this would get the partial negative, and this would get the partial positive. Okay, and then we can draw the oh goodness, dipole moment. Gosh, I forgot what I was saying for a second. The dipole moment for that bond. Oops, no hyphen there. Okay, and that dipole moment, all it does is show us which direction the electrons are going. So we could do this with any bond, all right? But when you put them into a molecule, things change a little bit. So let's just look at some really simple examples, okay? Let's start with carbon dioxide. So do the Lewis structure for carbon dioxide. And this one's simple because this molecule is linear, okay? And because it is linear, we don't have to think in 3 dimensions, so it makes it really, really simple. So if we look at a carbon-oxygen bond, it doesn't matter that it's a single bond or a double bond. Each one of these bonds is polar. So this carbon-oxygen bond is polar. We have a partial positive and partial negative if we just isolate one bond. And then same thing for the other one. And then we could do dipole moments for both of those bonds. So we have the electrons being pulled in this direction, and on the other side of the bond, or I'm sorry, on the other side of the molecule, they're being pulled in this direction. And we always put the positive on that arrow, indicating that it's going from positive to negative. Incidentally, they do it exactly opposite in Europe and the rest of the world. But anyway, that's the way we do it here. So what we have here is a tug of war for the electrons on carbon dioxide. One oxygen is pulling to the left, one oxygen is pulling to the right. So what do we find? This is a non-polar molecule. Okay, and that's because the symmetry in this molecule cancels the polarity. All right, so let's just look at another example of that. Let's look at carbon tetrachloride. So think about what carbon tetrachloride looks like. Four carbons. Remember, now this is in 3 dimensions, and it becomes more difficult when we start talking in 3 dimensions, because you have to imagine that molecule in 3 dimensions. This is where that PhET simulation can come in really handy, the simulator that I've linked in Blackboard. Okay, so now we can look at any one of these bonds, and they have a dipole moment. And the chlorine is partially negative, and the carbon is partially positive. Same would go for any of these bonds, okay? But watch what happens when we add the dipole moments, and I'll just do them all in different colors. Why? Because I have lots of different colors. No, I forgot the little positive. And there. Okay, so now it's really, like I said, it's really, really difficult to picture this three-dimensionally given the picture that I've drawn. But just imagine on that PhET simulator, we can rotate this any direction we want, and it's going to be exactly the same. There will be no difference one way or the other. So this ends up being a non-polar molecule as well. And why? It's because symmetry cancels out polarity. As long as it's symmetrical, it's going to be non-polar. Now let's look at an example. Let's just change that molecule above just a little bit. Let's make it carbon with a hydrogen and 3 chlorines. Okay, now that hydrogen-carbon bond, that's a non-polar bond. Okay, or that's a non-polar bond. These are still all polar. And again, we can go through and we can draw those dipole moments. Look which way those arrows, and for those of you that are familiar with vectors, this is just summing vectors, that's all it is. But if we look at those arrows that I've drawn, we get a net pull in one direction. Overall, the electrons are being drawn in this direction. That would be the net overall pull of the molecule, or of the electrons in the molecule. So this is a polar molecule. Oh, it's just one molecule. Okay, that's a polar molecule. And when I say polar, I mean it has a positive end and a negative end. We put a polar molecule in an electric field or a magnetic field, and the positive and negative will line up with the field. Okay. So let's just summarize here. So for a polar molecule, okay, to have a polar molecule, you have to have polar bonds and asymmetry in the molecule. Oh, I think I'm creating ways to spell asymmetry. If I'm spelling it wrong, oh well, you can't say anything, can you? Okay, sorry, I'm cracking myself up. And for a non-polar molecule, you know what, I'm going to change one thing here. Not really changing it that much. I'm going to emphasize the and. So for a non-polar molecule, you can either have only non-polar bonds, and what I'm going to emphasize here, is or you can have perfect symmetry, symmetrical molecule. Okay, so to summarize, polar molecule, you have to have a polar bond, at least one, and it has to be asymmetrical. Non-polar molecule, you have to have either only non-polar bonds or you have to have it be symmetrical.